is only the most recent of this theory's many triumphs. But while they are both highly successful, grand intellectual achievements, these two standard models are also riddled with holes. There's an awful lot they can't explain, and they leave a lot of important questions unanswered. If anything, their successes have only served to make the universe appear more elusive and mysterious, if not downright bizarre. The more we have learned, the less we seem to understand. The two theories are also fundamentally incompatible. In the classical mechanics of Isaac Newton, objects exist and things happen within a container of absolute space and time, which somehow sits in the background. If we could take everything out of Newton's universe, we must suppose that the empty container would remain. General relativity gets rid of this container. In Einstein's universe, space and time become relative, not absolute, and the theory is said to be background independent. Space-time is dynamic. It emerges as a result of physical interactions involving matter and energy. Quantum mechanics, though exasperatingly bizarre, yet unfailingly accurate in its predictions, is formulated in a different way. Interactions involving the elementary particles of matter and radiation are assumed to take place in precisely the kind of absolute space-time container that general relativity eliminates. Quantum mechanics is background dependent. And there you have it. We have a classical non-quantum theory of space-time which is background independent, and we have a quantum theory of matter and radiation which is background dependent. Our two most successful theories of physics are built on incompatible interpretations of space and time. They are woven on different kinds of fabric, one co-generated by the physics, and the other presupposed and absolute. We have two incompatible descriptions, but as far as we know, and certainly as far as we can prove, we've only ever had one universe. This is a problem because we also know that in the first few moments following its birth in the Big Bang, the universe would have existed at the quantum scale, at the mercy of a quantum mechanics. Now, the fact that we can't explain the origin and earliest moments of the universe might not trouble you overmuch, but the track record of physics in the past 100 years or so has encouraged us to have greater expectations. What we need is a quantum theory of gravity. So, do I have your attention yet? The Chinese philosopher Lao Tzu once said that a journey of 1,000 miles begins with a single step. The first thing we can do is recognize that the only way to bring together quantum mechanics and general relativity is to find a new fabric, a new way of conceiving of space and time, one that is compatible with physics on any scale. Charged with a newfound sense of purpose, we must now choose which road to take. Do we start with the presupposed absolute space-time fabric of quantum mechanics, or do we start with the co-generated fabric of general relativity? In the past 40 years or so, judgments concerning the ease of passage along these two roads have split the theoretical physics community along essentially tribal lines. This split is very visible in a recent attempt to map the relationships between all the different ways of developing a quantum theory of gravity, which identified two distinct fundamental branches: string theory and loop quantum gravity. This divide isn't simply the result of differences of opinion between general relativists and particle theorists, as theorists on either side frequently borrow ideas and techniques from both general relativity and quantum field theory. It is, however, true to say that the theoretical physics community is dominated by particle theorists, and particle theorists tend to favor the string theory approach. In the past 20 years or so, their highly successful PR has spilled into the popular science literature, with the result that few readers are even aware that there's more than one game in town, or more than one road that can be taken. For example, in one recent popular book about gravity, loop quantum gravity is mentioned only in passing, relegated to a footnote. There are all sorts of reasons for this, and I will discuss some of these in what follows. This book is about the road less traveled. It starts from general relativity, borrows ideas.